Welcome to this presentation on rate equations. Rate equations show how the rate of a chemical reaction depends on the concentration of reactants. They help chemists understand which substances affect the reaction speed and by how much. Specification, context and importance of rate equations, defining the rate equation and its components. Rate equations directly on earlier work on rates of reaction and collision theory, but move beyond qualitative descriptions into quantitative, mathematical modeling of reaction rates. The topic integrates experimental design, data analysis, algebraic manipulation, and graphical interpretation, making it central to Paper 2 and Paper 3 assessments. Rate equations explain how changes in reactant concentration affect the speed of a reaction at a fixed temperature. A rate equation describes how the rate of a chemical reaction depends on the concentrations of reactants at a constant temperature. The overall order of reaction is the sum of the individual orders. The rate itself is defined as the change in concentration of a reactant or product per unit time and is typically measured in mol dm cubed s to the power of 1. Understanding zero, first, and second order reactions, the initial rates method explained, worked example, determining orders from data. The order of reaction with respect to a reactant indicates how changes in its concentration affect the reaction rate. A zero-order reaction shows no change in rate when the concentration of that reactant changes. This often occurs when a catalyst surface is saturated or when another factor is limiting. In a first-order reaction, the rate is directly proportional to the concentration of the reactant, so doubling the concentration doubles the rate. In a second-order reaction, the rate is proportional to the square of the concentration, meaning that doubling the concentration increases the rate by a factor of 4. The initial rates method involves measuring the initial rate of reaction for a series of experiments in which the initial concentrations of reactants are systematically varied. By comparing pairs of experiments where only one reactant concentration changes, the order with respect to that reactant can be deduced. Worked examples are essential for developing confidence with rate equation questions. Consider an experiment where the concentration of reactant A is doubled from 0.10 moles dm cubed to 0.20 moles dm cubed while the concentration of B remains constant, and the rate increases from 0.02 to 0.08 moles dm cubed s to the power of 1. The rate has increased by a factor of 4, while the concentration has doubled, indicating second-order dependence on A. Overall order and the rate constant K, units of the rate constant and their significance, concentration, time graphs, and order identification. The overall order of a reaction is the sum of the individual orders with respect to each reactant and provides insight into how complex the reaction kinetics are. The rate constant K is a proportionality constant that relates the rate to reactant concentrations at a given temperature. Its value reflects how fast a reaction is under specific conditions and changes with temperature but not with concentration. The units of the rate constant K depend on the overall order of the reaction. For a zero-order reaction, K has units of mol dm cubed s to the power of 1, the same as rate, because rate is independent of concentration. For a first-order reaction, K has units of s to the power of 1, reflecting the proportional relationship between rate and concentration. For a second-order reaction, K has units of dm cubed mol to the power of 1 s to the power of 1. Zero-order reactions show a straight-line decrease in concentration over time because the rate is constant. First-order reactions show an exponential decay curve, with concentration decreasing rapidly at first and then more slowly. Second-order reactions show a more pronounced curvature. Students must be able to recognize these shapes and link them to kinetic behavior. These graphs also help explain why first-order reactions have a constant half-life, while zero- and second-order reactions do not. Half-life and first-order reactions, the Arrhenius equation and activation energy, Arrhenius plots and determining activation energy. Half-life is defined as the time taken for the concentration of a reactant to decrease to half of its initial value. This property arises from the exponential nature of first-order kinetics and provides a useful method for identifying reaction order. The mathematical relationship T equals 0.693 K must be known and applied confidently. The Arrhenius equation, K equals AE, links the rate constant to temperature and activation energy, providing a quantitative explanation of why reactions speed up at higher temperatures. As temperature increases, a greater proportion of molecules have energy equal to or greater than EA, increasing K. An Arrhenius plot is a graph of ln K against 1T. This graph is linear, with a gradient equal to EA/R, allowing activation energy to be determined experimentally. Reaction mechanisms and the rate determining step, required practical 7, investigating rate equations, exam techniques, common mistakes, and summary. Reaction mechanisms describe the sequence of elementary steps by which reactants form products. The rate-determining step, RDS, is the slowest step and controls the overall rate. Only species involved in or before the RDS can appear in the rate equation. Intermediates formed after the RDS do not appear. Required Practical 7 focuses on investigating the effect of concentration on reaction rate, often using clock reactions such as the iodine clock. Students must be familiar with the experimental setup, variables, and data analysis. The practical reinforces the initial rates method and helps students understand how experimental evidence supports rate equations. Success in rate equation exam questions depends on clear structure, correct terminology, and logical reasoning. To summarize, rate equations show how concentration affects reaction rate. Reaction orders are found experimentally, and rate equations help us understand reaction mechanisms and control reaction speeds. Thank you for watching.